Welcome to number theory. In this video, we'll take a look at what number theory is and why we might be interested in it. So what is number theory? It's the study of integers and all of their properties. So you might be thinking to yourself, didn't I learn about this in primary school? I've worked with all of the integers, negative, positive, I've even played with zero. So what more could there be to learn? The key areas that we will be exploring include divisibility and modular arithmetic, as well as primality and relative primality, as well as different ways that we can represent integers, such as binary numbers, hexadecimal numbers. This topic has been around for a long time. Let's start with divisibility and modular arithmetic, which is a great place to begin. As we explore this topic, we'll start off with a quick review of some facts that we hold to be true, and then we'll take a look at divisibility and some division algorithms, as well as modular arithmetic. First, we'll go through a few reminders. The first piece is divisibility. We just recall that if a and b are integers and a is non-zero, then we can say that a divides b, and we denote it as a with a line b, a divides b, if there exists an integer k such that b is equal to k times a. That means that a is a factor or a divisor of b, and b is a multiple of a. If a does not divide b, we denote it with that division symbol with a line through it. And so if we look at our examples, we can see that 7 is not a multiple of 3. And so 3 does not divide 7. But we know that 12 is equal to 4 times 3. And so 3 does divide 12. 5 is not a divisor of 24. And so 5 does not divide 24. 13, on the other hand, is a factor of 52 because 52 is equal to 4 times 13. And so 13 does divide 52. The other properties that we want to remember are some of those properties surrounding divisibility. So if we have three integers, a, b, and c, and again, we'll let a be non-zero, then if a divides b, b over a is an integer. We know that because b is equal to some multiple of a. And so we should get back that factor. If a divides b and a divides c, then a should also divide b plus c. And you can motivate that by the fact that b must be some multiple of a, c must also be some multiple of a. So b plus c is ka plus ja in my example over a. You can pull the a out and you're going to end up with the sum of those two factors. If a divides b and b divides c, then a also divides c. And that's also straightforward to see. If a divides b, then b is equal to some multiple of a. And if b divides c, then that means that c is equal to some multiple of b. But because we know that b is a multiple of a, we can also say, well, then we also have that c is a multiple of a. If a divides b, it also divides b times c. That one's fairly clear. You can put those together and get a larger result, but for the most part, we just want to remember how divisibility works and what we can do with it. All right. So you're pretty good at divisibility. You've been doing it since primary school. Quick. Is the following number divisible by 7? Well, doing this quickly is not always as simple as it sounds. However, being able to solve this quickly and efficiently is crucial to areas like cryptography. And so we're going to learn a little bit more about how we can speed that process up, and we'll start by looking at the division theorem. The division theorem says that if we have an integer n and a positive integer k, then there are unique integers d and r such that we can represent n as d times k plus r, where r is specifically greater than or equal to 0 and less than k. And in fact, we know further, and we've looked at in the past, that d is the floor of n over k and r is n mod k. And you remind yourself that n mod k is the remainder when you take n and divide it by k. And what's important about the division theorem is it tells us that these values that we get, they're unique. They exist and they are unique. And within this, we call n the dividend, d the quotient, k the divisor, and r the remainder. So if we want to look at an example, if we wanted to find d and r, where we're looking for n equals d times k plus r, for an example where n is equal to 579, k is equal to 111, then we're trying to look for a unique d and a unique r such that r is greater than or equal to 0 and less than 111. And we said that this is going to be, d is going to be the floor of n over k, and r is going to be n mod k. And so in this case, that means d is the floor of 579 divided by 111, and r is 579 mod 111. The way that we find that, remember, we call this the dividend, quotient, divisor, and remainder. And so it's that for a reason. So n is our dividend, n, and so that's that 579. And the divisor is k, our 111. And when we divide n by k, what we get is the quotient, d, and then some remainder, r. And that is what is used in this equation. So that is why it's unique. When you divide a number by another number, you get an answer, a quotient, and a remainder. And they are unique. And the remainder is always going to be less than k, because if it weren't, you could have always increased your quotient by 1. So if we take a look at our example, 579 divided by 111, we can see that it fits in 5 times. We can fit 555 into 579, but we can't fit 666. So it fits in 5 times, but there is a remainder. When I take 579 and I subtract 55, I can see that I'm going to get a remainder of 24. And so the floor of 579 divided by 111 is going to be 5. 579 over 111 is 5 point something. So the floor of that is 5. And if I look at 579 mod 11, well, that is the remainder when I divide 579 by 111. And so our r is equal to 24. And so we know then that our number 579 can be expressed as 5 times 111 plus 24. So dividing like that will get you there, but it's a bit tedious. It's called longhand division for a reason. And so can we think of other ways that we can approach this? Well, one way would be to use a division algorithm to compute the floor of n over k and n mod k. And the idea behind this particular division algorithm is that we're going to repeatedly subtract k from n until we reach a number in the range 0 to k minus 1. We need that remainder to be small enough that it's less than k, and so we just continue to repeatedly subtract from n until we get to that range. So an example of what that looks like, and here's an algorithm, mod and div. It takes as input two integers, n greater than or equal to 0 and positive k. And it's going to output the values of d and r that we're trying to calculate. So the floor of n over k, the quotient, and n mod k, that remainder. And the way that it does that, so we're starting with the same n and k, 579 and 111. And the way that it does it is it starts by setting r to n and d to 0. And so we'll go ahead and do that. R is going to be set to 579. D is going to be set to 0. And then it's going to iterate through this loop structure while r is greater than or equal to k. So we check, is r greater than or equal to k, which is 111? It is. 579 is greater than 111. And so we enter that loop. And so we're going to run lines 4 and 5 as long as r is greater than or equal to 111. And so what we do on that next iteration is we set r to r minus k. So we're going to subtract 111 from our r, and we get down to 4, 6, 8. And then, as we see on line 5, we're going to increase d by 1. So d will go up by 1. And then we check, is 468 greater than or equal to 111? It is. And so we will once again subtract 111 and increase d by 1. 357 is still too big, so we'll subtract 111 to 46 and bring d up by 1. Back to the top of the loop, do our quick check. 246, still bigger than 111. Subtract, we get down to 135, increase d by 1, and check again. 135 is still too big, so we're going to subtract again, and this becomes just that 24. D becomes 5. And now this time when we come back up to line 3 and we check, is r greater than or equal to k? It is not, because 24 is less than 111. And so that at that point, we drop down to line 6, and it says return d and r. And so we return from this algorithm with d equal to 5 and r equal to 24, which is the answer that we got before. So the division theorem restated said that if we had integers n and positive integer k, then we could express n as the floor of n over k times k plus n mod k. And that was what was returned from this algorithm, div and mod. So the number of steps that it took to answer, right? If we look back at our calculation, we stepped through this algorithm. It took us exactly d steps to get to that answer. And the question is, do we need it to be faster than this? What if you're checking if you have the number 123,456,789 and you're checking to see if that is divisible by 7? Well, that is going to take the floor of 123,456,789 divided by 7. So that's more than 70 million divided by 7, which the floor of that would give us 10 million iterations. That's a lot of iterations. So the question is, though, that was a big number. Is that fast enough? The answer is no. We can do better. A generally accepted definition of efficient would be that it required a number of steps that is polynomial with respect to the size of the input. but the size of the input is different from the input itself. So the size of this input is 9 characters. The number is over 123 million, but the size of the input is just 9 characters. And so we would expect and hope that we could find an efficient algorithm that is polynomial with respect to the size of the input. So if we had input of size n, then we would expect to be of order n to the c, to some constant. So this is not fast enough, but it will eventually get us there. Let's remind ourselves of some properties of modular arithmetic. So we remember that n mod k is the remainder when we divide n by k, but let's remind ourselves that k mod k, it's always 0. The remainder when you divide a number by itself is always 0. And then we also have these other fun features. If we take a plus b mod k, then it is the same as a mod k plus b mod k, all mod k. And we can't forget that mod k at the end because we get a very different answer if we do. If we have a times b mod k, then that's the same as a mod k times b mod k, all mod k. And a to the bth power is a mod k to the b mod k. With that in hand, now can we check if this number is divisible by 7? Well, if it's divisible by 7, then if I take it mod 7, we should get back 0. We can take a look at each piece because I know that if I take 28 to the 24th mod 7, this is equal to 28 mod 7 to the 24th all mod 7. And that might look like a lot to figure out, but I know that 28 is a multiple of 7. And so this piece in the middle, this is 0 to the 24th mod 7. But that's just equal to 0. And so we can see pretty quickly that this left hand portion of that calculation is going to go away because the very first thing we're going to get is 0 times 5 cubed mod 7. And so I don't even have to deal with this left-hand side. And so this whole thing becomes 2 to the 6 mod 7 times 3 mod 7 all mod 7. But I can go a bit further because I know that this then becomes 2 mod 7 to the 6th power mod 7 times 3 mod 7 mod 7. It's a lot of mod 7s, but now they quickly go away. 2 mod 7 is 2, and so this becomes 2 to the 6 mod 7 times 3, because 3 mod 7 is 3. 2 to the 6 is 2, 4, 8, 16, 32, 64 mod 7 is just 1. So this becomes 1 times 3 all mod 7, which is just 3. And importantly, this is not equal to 0. So is this divisible by 0? The answer is no. Where in the world are we going with this? Have you ever played the game Geography where I take a place in the world? So you might give me Alberta, which ends in the letter A. And in the game of geography, that means that the next word that I have must start with the letter A. So you might trick me and give me another word, Alaska, that also ends in an A. And I want to get out of that loop. And so I can say Azerbaijan, oops, which ends in an N, and you come back with Nova Scotia, which also ends in an A. And this can keep going, and whatever that last letter is drives the next one. And the reason I bring up this game is what we see is no matter what we do, we're going to end up playing on the same circle of the alphabet A, B, C, D, E, all the way around until we get to X, Y, Z, and then returns to A. But I'm always going to stay on this circle, right? I'm going to start with an A for Alberta. I'm going to come around and I'm going to end back at that A. And you're going to be able to reach any other point on the circle by choosing a place that ends in the appropriate letter. And so there's a function that takes in this place name and then returns a letter, and that it just does that by returning the letter that is the last letter of the word. So that's a fun game to play, but we'll come back to it. There are other ways that we can play. There are other games that we can play mathematically that do exactly the same thing. So for some integer n greater than or equal to 2, we can actually define this set 0 to n minus 1 of integers by this z subscript n. And that is the set of integers that we can reach if we're working modulo n. So when we work mod 2, then the numbers that we can reach are the binary numbers 0 and 1. The numbers that we can reach are the numbers 0 and 1. If we work mod 3, then the set of integers that we can reach are those integers 0, 1, and 2, and so on. And so just as there was congruence around the globe, Alaska, which ends in an A, acted the same as Alberta, which ended in an A, acted the same as Nova Scotia. The same can be true of certain numbers when we work modulo another number. So for instance, when we're working modulo 3, we say we're always going to end up returning one of the numbers 0, 1, or 2. So if I have a number 2 mod 3, this acts the same as 5 mod 3, which acts the same as 8 mod 3, and it's equal to many other numbers. But because this always acts like 2, so we always return that 2. And likewise, if I look at 1 mod 3, this behaves the same as 4 mod 3 and 7 mod 3, and so on. And so we have these sets of numbers that behave the same modulo another number, in this case 3. So what that means is we have a set of numbers that all behave the same. And so this is called congruence over Zn. And we say that a letter A is congruent to B modulo M if we look at the difference between those numbers and see that that's a multiple of M. So the way that this is denoted is either A is equivalent to B modulo M, or A is equivalent modulo M of B. So these two integers are congruent modulo M if and only if A mod M is equal to B mod M. And that is, they both have the same remainder when we divide by M. So let's take a look at a quick example. If we want to determine whether 17 is congruent to 5 modulo M, we can look at that difference. We can say 17 minus 5, that's 12. 12 is divisible by 6. So we assume that 17 is is congruent modulo 6 to 5. Likewise, we can check if 24 and 13 are congruent modulo 7. And we can say, do you know what? 24 minus 13, that difference is 11. That is not divisible by 7. And so 24 is not equivalent modulo 7. And the reason for that is as follows. 17 is equivalent to 5 modulo 6 because 6 divides 17 minus 5. And 24 is not equivalent to 13 modulo 7 since 24 minus 13, as we said, was 11, and this is not divisible by 7. So that's it for divisibility and modular arithmetic. But on to primality.